All right, so this is an ALEKS topic that's called calculating equilibrium composition from an equilibrium constant. And this is a really good basic ice table equilibrium constant type problem. The one aspect about this problem that is sort of more difficult or confusing is that we're going to have to solve for x exactly. If you are familiar with these types of problems and you've been working with ice tables, you know that a lot of times we can treat the x value sort of as negligible, but in this case we can't, and that's what makes this one a little bit more challenging. So let's go ahead and get into this, and I'll walk through the steps and how we sort of know that. So the first thing is that we're told that we've got a 500 milliliter flask, so we might draw a little picture of our 500 milliliter flask. And inside of that 500 milliliter flask, we've got our N2 and O2, and so we're going to see that they're all gaseous, so maybe I shouldn't have drawn a liquid here. Maybe we're going to stopper this up, and we're going to have our gases moving around in this flask. So then it says the following reaction becomes possible. N2 plus O2 creates nitrogen monoxide, so we're going to get this other gas. We are given an equilibrium constant K. So whenever I see this equilibrium constant, I think it's going to be a good idea to write out the equilibrium constant expression. We have an equilibrium reaction here. Now I'm going to write a Kc. The reason I'm choosing Kc is because I'm given moles and liters. So molarity is sort of the most obvious thing to be thinking about there. Since we have gases, we could also be using a Kp, but if that doesn't make sense to you, if you've never heard of that, don't worry about Kp. It's just sort of another way to do these types of problems. We can always use Kc though. NO squared, so this coefficient, that's going to become the squared here, over the concentration of N2 times the concentration of O2. That's going to be my equilibrium constant expression. And we have a value for that of 0.614. Now right away I'm sort of noticing this value of the Kc is not really, really big or really, really small, and that's going to sort of tell me that this equilibrium is going to be somewhere sort of in the middle. It's not going to favor one side over the other, and that's going to be the reason why we can't use that sort of treat this x as negligible, why we're going to have to solve for x exactly using the quadratic formula. Dun, dun, dun. Okay. The next thing that I'm going to want to do is figure out where I'm at. So figure out with these starting initial concentrations what that's going to do to the reaction. So I might write out, so let's do it over here. N2 plus O2 is in equilibrium with 2NO. And we're going to use our ice table. So we know that we need to use an ice table since it's equilibrium. And I can convert essentially this 0.1 moles of N2 into a molarity of N2. I always want to be using molarities in my ice tables. Now you can use moles, but I just think it's a better practice because over here in my Kc expression, I always want to be using molarities. I'm just going to always use molarities for my ice table. So my initial molarity here would be 0.200 molar N2. I've got 0 O2, so if I look here, I've got this 0.1 moles. Converting that to molarity using 0.1 moles divided by milliliters gives me there. And then for my NO, that's going to be 1.00 molar. I'm not going to be too worried about sig figs in this problem. I'm showing 3 sig figs. That is actually improper now that I see that I've got 2 sig figs here. So two sig figs is better for these numbers. When I do these types of problems, I don't worry about sig figs till the very end. Carry all your digits as you go through the problem, and then just worry about the sig figs at the end. Okay, this reaction is going to shift to the left. And I know that this reaction is going to shift to the left because I have 0 O2. The fact that I have 0 O2, well, that makes it impossible to shift the reaction to the right. In order to get to equilibrium, I'm going to be always shifting in the direction where I've got 0 of something. If I have some quantity of everything here, then I'm going to have to think about reaction quotient and all that sort of stuff. Okay, reaction shifts to the left, plus x minus 2x. Don't forget that minus 2x because of the 2 coefficient there. So then at equilibrium, I should have 0.200 plus x for my N2. I should have x for my O2, and I should have 1.00 minus 2x for my NO. Now I can plug these equilibrium expressions, equilibrium values in for my Kc. So getting up here, this is going to be 1.00 minus 2x squared. All right, the video cut off there, but I went ahead and finished plugging in my values for my equilibrium expressions into my equilibrium constant. So 1.00 minus 2x squared, again, don't forget that's squared. 0.2 plus x, that's going to be my concentration of N2, and then my x value for O2. And all of that should equal 0.614. So what we have here is one equation with one unknown that we need to solve for. Now, sometimes in these equilibrium constant expressions, we're able to sort of treat this plus x or minus 2x as negligible, and it makes it a lot easier to solve the problem. Now, in this case, that is not one of those cases where we can do that. So we have no shortcuts. We need to solve this problem as is. So there's a number of ways you can do this. If you have a TI-89 calculator, so this is my trusty old TI-89, you can actually use a solver function on a TI-89 and just plug this value in just this entire thing. If you're familiar with other math solver programs online, you could also just do the same thing here. If you're not familiar with those and you don't have access to something like that, then what we need to do is we need to do a bunch of algebra and then use the quadratic formula. So I'm going to do both. So the first thing I'm going to do is I'm going to say, well, what I did, and I think a nice method that if it's available to you to use is to plug this whole thing in, figure out how to do that on your calculator, figure out how to do that online, and solve for x. If you do that, you're going to end up with an x value of 0.883 or 0.334. So either one of these x values is going to solve this equation and give you an answer, essentially. So then you need to decide, well, which one should I use? Which one is going to make sense? They both seem like reasonable numbers. Sometimes when we do this, we're going to get one number that's a positive number, one number that's a negative number. Obviously, in that case, we'll use the positive number. But in this case, what we need to do is we need to check which one of these numbers makes sense or is valid with what we have written over here. If I take 0.883 and I plug that in as my x value, well then my concentration of NO is actually going to become negative, and that does not make sense, right? We cannot have a negative concentration. 2 times 0.883, that's going to be 1.6 something. 1 minus that value will give us a negative concentration. So I know right away it cannot be this 0.883, it must be this 0.334. Now, that's actually going to be our final answer in this problem. So what we are actually looking for is the equilibrium molarity of O2. When I solve for x, that x value, that is actually the equilibrium molarity of O2. Another good reason to use molarities in our ice table instead of moles, we're getting our answer directly. So in this case, I would take this 0.334. It says round your answer to 1 decimal place. So that's going to be 0.3. That is my final answer, and we've got our molarity unit there already. Now, in terms of simplifying this, I know that some people might want to see how to do that, so I'm going to do that really quickly. All right, so if I wanted to solve this using algebra and the quadratic formula, I'm going to start by rewriting my equilibrium constant expression, 1 minus 2x squared over 0.200 plus x times x. The first thing I'm going to do is I'm going to expand both of these. So sort of start breaking down the parentheses. So 1 minus 2x squared, that's going to end up giving us 1. I'm going to forget about sig figs while I write this out. 1 minus 4x plus 4x squared. So that's just the expansion of this 1 minus 2x squared. That gives us this. I'll do the same thing. This is really more a distribution of this x. 0.2x plus x squared. That's going to be what's on the bottom. And that is still going to equal this 0.614 on the left-hand side. The next thing that I would do is I would bring this, sort of multiply both sides by this 0.2x plus x squared to get rid of this. So if I multiply this side by 0.2x plus x squared, those are going to cancel. And I need to do the same thing over here, 0.2x plus x squared. So then I'm going to do the same sort of distribution on the left-hand side. I'm going to get 0.1228 times x plus 0.614x equals, x squared. It's easy to make little mistakes, so when you're doing this process, try to go as slowly and deliberately as you can, because if I forgot that x squared, right, then I would have been screwed. So I got to make sure that I'm keeping everything intact. Then the right-hand side will just be 1 minus 4x plus 4x squared. And now I can sort of start grouping things together. So in my mind, it makes more sense to bring these things over to the right-hand side. So I would, this would be minus 0.1228x minus 0.614 x squared on this side. So then I'll end up with 0 equals 1 minus 4.1228x, and then plus 3.386x squared. So now this is ready for the quadratic formula. This would be my value for A, this would be my value for B, this would be my value for C. So A would equal positive 3.386, B would equal negative 4.1228, and C would equal 1. And again, I can plug this in as a quadratic formula on my calculator. I can use an online tool. You could actually do the quadratic formula by hand. I'm not going to do that in this video. There's lots of different, you could graph it, right? There's lots of different ways to solve this for x. And again, when you do solve this for x, you're going to end up with the same two values. X should equal 0.334 or 0.883. And we need to decide which one of those is going to be the value that we're going to use, right? So going back over here, we want to choose the 0.334. So this is this problem. It's definitely a more involved problem. I think the first part of it is really great, and then actually doing the algebra, solving it, it's good practice. So let me know if you need any more help. All right, thanks a lot.